Hello, and welcome to the next part of the course. In this module, we will walk you through another complete process from end to end of modeling a flow distribution in a manifold. The flow distribution in manifolds is highly dependent on the inlet pressure, configuration, and total inlet flow to the manifold. Flow in the manifold is of great importance in many industrial processes, when it is necessary to distribute large fluid stream into several smaller streams and then to collect them into one discharge stream. Manifolds can usually be categorized into one of many types such as dividing, combining, parallel, and reverse flow manifolds. Parallel and reverse fold manifolds are those that combine dividing and combining flow manifolds and are most commonly used in plate heat exchangers. A uniform flow distribution requirement is a common issue in many engineering circumstances, such as plate type heat exchangers, piping systems, heat sinks for cooling of electronic devices, fuel cells, chemical reactors, solar thermal collectors, flow distribution systems in treatment plant, and the piping system of pumping stations. Therefore, for most applications, the goal of a manifold design is to achieve a uniform flow distribution through all the lateral exit ports. A great number of experimental, analytical, and numerical studies deal with flow in a manifold. So, in this module, you'll learn how to model and analyze the flow distribution in a very typical manifold. Let's get started. As usual, before you start the modeling process, you should have a clear goal in mind. That is, what are you trying to achieve from this model? The answer to this question would form a skeleton guideline for you through the modeling pre-process and post-process. And clearly, our goal in this particular situation is to test if the design would achieve a uniformly distributed flow at all different outlets. Let's open Workbench. Once the Workbench has opened, on the left panel, scroll down to Mesh and drag it to the Workbench schematic window. Right-click on the geometry and locate the geometry file, which has been given to you from this course. It's optional to view the geometry in ANSYS Space Claim. Or you can go directly to the mesh by right-clicking on the mesh and choose Edit. Once the mesh window has opened and loaded with the geometry, we will perform a very quick meshing. First, we will create some name selections. Select the critical surface perpendicular to the global Z axis and create a name selection. We'll name this as Inlet. This is the inlet flow of air, which is 60 litres per minute. Select the first circular surface perpendicular to Y, closest to the inlet, and create a name selection for this. Name this as Outlet 1. This is the first outlet flow. Repeat the process and create other outlets from 2 to 6. Ideally, we want the same flow rate at these outlets. Let's see if we can achieve this through the design. Last one, select all remaining surfaces and create a name selection. Name this as Wall. Next, click on Mesh and choose Physics Preference to CFD, as we are doing a CFD simulation. To adequately resolve flow gradients near the wall, we require a smaller mesh near the wall. An efficient way to achieve this is by inflating the wall surface mesh to produce layers of thin prismatic cells called inflation layers. As a final but very important step in the meshing tool, we will now enable the automatic creation of inflation layers from all walls. In the outline tree, I will click Mesh to display the details of the mesh panel. Having completed my inflation setup, you can see from the magenta color of the mesh that the mesh is obsolete and needs to be generated again. So, I will right-click on the mesh in the tree and select Generate Mesh. Notice that the program-controlled inflation has automatically created prismatic layers from all the walls, and this can be traced by the quadrilateral mesh faces on the 4 surfaces that are associated with name selections. To make this more obvious, I will show the mesh elements in the interior of the domain by using the selection planes. Click Selection Planes in the toolbar. I will then define a section plane by holding the left mouse button and drawing a line through the model geometry. Rotating my model to expose a section plane, I can see the intersection of the mesh with the section plane. To make things clear, I will click here on the Section Plane panel. This icon will enable Show Whole Elements, and you now can see the prismatic elements created on all walls, running through the inlet as well as the 6 outlets. You will learn more details about inflation later in the course. One final thing to do before going to Fluent Setup is to check the mesh quality. Expanding the quality part of the details of the mesh panel, I will select orthogonal quality as the mesh metric. We can see here that the minimum orthogonal quality is higher than the lowest acceptable value of 0.1. You will learn more details about mesh quality later in the course. As we have generated a good mesh, we will now close the meshing tool and return to the project page. We do not need to save this, just close the mesh window. ANSYS Workbench will take care of the saving. Back to the ANSYS Workbench schematic window on the left panel, scroll down to Fluent and drag it on the mesh. Then right-click on Mesh and choose Update. What this does, behind the scenes, is that ANSYS links the mesh that we have generated before with the Fluent solver setup, so that the solver can perform the CFD simulation. Double-click on Setup and bring up the Fluent window. Let's go ahead and set up the model in ANSYS Fluent really quickly. Remember, the problem statement for the manifold is that we have air coming in the inlet at 60 litres per minute, and I want to see whether or not the 60 litres per minute is uniformly distributed between the 6 outlets. Now, as the graphic window has opened and the geometry is displayed, you can see that the ribbon is organised into a number of tabs. A typical workflow is that you go from the left tab to the right, starting from Domain, then Physics, then Solution, and finally the result. Obviously, you can go back and forth. However, if you make a habit of going from the left to the right, you'll not miss anything. Now, click on Domain. The very first task I usually perform is to do a mesh check. If you can see the bottom display saying that the mesh check is done, then it is OK to proceed. Otherwise, a mesh check failure message would have been displayed. In that case, you would have to re-examine the mesh and correct it. Next, in the Physics tab, note that within each tab, I will also have the habit of going from the left to the right so that I will not miss anything. Under the solver setting, I will leave everything as default for now. Under Models, I do not need to tick on energy because I am not worried about the temperature in this problem. Materials are next. I will just click on Create/Edit to show you what this looks like. By default, the fluid is air, but later in the course we will also show you how to work with other materials such as water, gases or other liquids, and also how to change the property of fluids such as density and viscosity. But here I just want to use air with the default properties. So I will just close the panel. Again, moving to the right, there are zones and boundaries. This problem will keep the defaults for cell zones, so I will skip that. But I'll go and set up the boundary zones, so let me click on Boundaries. The boundary panel opens up and a list of boundaries are displayed. Boundary conditions will be described in more details later. For now, I'll need to define the boundary conditions for the inlet, the outlets, and the walls. You can see other boundaries in a list whose names start with interior. But actually, they are not boundaries. Instead, they are actually a list of collections of faces between neighbouring cells. And no boundary condition is ever applied to these faces. So, for now, I can safely ignore them. Again, we'll talk about them in detail later in the course. But we'll need to set boundary conditions for the inlet. So, let's just double-click that. The velocity in this case is 1.974 meters per second. This number comes from the fact that the mass is equal to the volume multiplied by the density. We know the air density and we need 60 litres of air per minute. So it will be equivalent to 1.974 meters per second. This is quite easy math. The outlets are all going to be set to the default 0 gauge pressure. We can just open this one and look, but no changes are needed here or in either of the other 5 outlets, since the energy equation is not being solved. There is also no need to enter any conditions for the wall, so that is all for the Physics tab, and next I will move to the Solution tab. For this problem, all the default settings under Solution and Controls will be used, which is normal for most cases. I want to define a report definition to help monitor convergence in this case, since we are interested in the flow distribution at the outlets. I will select volume flow rate for the report type. We will enter a name for the report outlet flow rate. This is not a requirement, but if we ever have to open this model again in the future, it will help to understand what model it is. We are interested in seeing the values from all 6 individual outlets, and we can use the per surface option so that when the solution is running, each outlet will have its own curve in the report plot. I will also activate the report file and the report plot. We can click OK to finalize the report definition, and then we just need to click on Initialize. Again, remember that the information displayed in the console window about the initialization progress is normally not too useful. We will enter 1000 iterations and click Calculate, and then when it begins to calculate, I will go to the sub-window view so that we can see the report plot and the residuals at the same time. And notice in the report plot, there's one curve for each of the 6 outlets. Okay, so once the solution is finished, you can see the report plot curves are all flat and the residuals have reached the default criteria. We can move to the Results tab and begin post-processing. First, let's look at the mass balance and remember that this is in the Reports group under Fluxes. We will go to the Results tab to view the solution. Over the course, you will learn about many post-processing features available in the Results tab. Here I only want to show you a couple of things, namely how to show mass balance and how to plot a path line flow profile. Mass balance can be shown by clicking Flux Report. Select Inlet and Outlet and click Compute. The report will show the mass at the inlet and outlet. Fluent uses sign convention so that positive sign means fluid is entering the domain. Negative sign means the fluid is exiting the domain. What this means is that if you select all the inlets and outlets and then add them all together, the net result should be 0. And this is what is seen at the lower corner of the panel. Because CFD is a numerical method, the net results would never be exactly 0. However, this tolerance could be accepted as accurate. Next, let's look at some graphs. Notice in the report plot there is not a very uniform distribution of the flow between the outlets, so maybe it would be interesting to try to investigate why that might be the case. The first thing I'll do is make a mesh object in the ribbon under the graphics group. I can click Mesh and then New to make an object in the Mesh Object panel. I'll turn off the edges and click Save Display. This is the mesh object, and we will right-click in the graphics window to say that I want to create path lines. We can change the path lines to be coloured by time, and I will release them from the inlet and then click Save Display. You can now see the path lines in the graphics. The significance of colouring by time is that it can sometimes help to identify recirculation zones, or other regions of the domain where poor flow behaviour may be present. So now with the path lines and the mesh object, we can create a scene. I will select both objects and add some transparency for the mesh object in order to be able to see what is happening inside. Click Save and Display. Once it is displayed, I can orient the view, and you can see here it looks as though the flow from the inlet simply overshoots or bypasses the nearest outlet and goes mainly into the other outlets. It also creates this large recirculation zone, so by observing the flow pattern, this can help give you ideas for how you might want to modify the design to try to achieve a more uniform flow distribution through each of the outlets. You do not need to explicitly save any Fluent files. Workbench will take care of that for you. All you need to do is close Fluent and save the Workbench project file. Note that there is now a tick at the Setup and Solution cells in Fluent, indicating these are up to date. This is the end of the video. See you in the next module.